Tonight, we're going to explore something you probably heard 1,000 times, but never truly understood. In space, no one can hear you scream. You've seen it in movies, you've read it in books, but here's what almost nobody realizes. The reason you can't hear anything in space isn't just some quirky fact about the cosmos. It reveals something profound about the very nature of sound itself. Because sound isn't what most people think it is. It's not some invisible force that flows through the air. It's something far more physical, far more mechanical, and far more dependent on the world around you than you ever imagined. And once you understand why space is silent, you'll never hear a single sound the same way again. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something so familiar you've probably never thought about it. Sound. You hear it every day. You hear it right now. Whether it's the hum of your refrigerator, the low murmur of traffic outside, or the sound of your own breathing sound is one of the most constant features of your life. From the moment you're born to the moment you die, you're surrounded by it. Sound wakes you up in the morning. It tells you when someone's at the door. It carries the voices of people you love. It delivers music that moves you to tears. Sound is so woven into your existence that you almost never stop to think about what it actually is. And that's the problem. Because most people have a completely wrong idea about sound. They think of it as something that just exists, like air or light. Something that's simply there. You speak, and the words float across the room. A car honks, and the noise reaches your ears. A bird sings, and the melody drifts through the park. It all seems effortless, automatic, like sound is some kind of invisible substance that fills the space between things. But that's not what sound is. Not even close. Sound is a physical event. It's a mechanical process. It involves real matter doing real things. And if you want to understand why sound can't travel through the vacuum of space, you first need to understand what sound actually is at its most fundamental level. Because once you see what's really happening every time you hear anything, the silence of space becomes not just understandable, but inevitable. Let's begin at the very beginning. Imagine you're sitting in a completely still room. No wind, no movement, no sound at all. The air around you is calm. Now, the air in this room is an empty space. It's filled with molecules, mostly nitrogen and oxygen, with tiny amounts of argon, carbon dioxide, and a few other gases. These molecules are incredibly small. A single nitrogen molecule is about 3/10 billionths of a meter across. You can't see them. You can't feel individual ones, but they're there, in enormous numbers. In a single cubic centimeter of air, roughly the volume of a sugar cube, there are approximately 25 billion molecules. That's a 2 and a 5 followed by 18 zeros. In a single breath, you inhale roughly 25 sextillion molecules. These molecules aren't sitting still. Even in perfectly calm air, they're moving constantly, bouncing around in random directions at speeds of about 500 meters per second. They collide with each other billions of times per second. The air around you is a frenzy of invisible activity, molecules crashing into each other, bouncing off walls, ricocheting in every direction. You don't feel this chaos because the molecules are so small and so numerous that their collective effect averages out to stillness. Now, into this calm room, introduce a vibration. Any vibration will do. Clap your hands. What happens? When your palms come together, they stop suddenly. The air molecules directly in front of your hands have nowhere to go. They're pushed forward, compressed into the molecules in front of them. Those molecules are now bunched together, packed more tightly than they were a moment before. This region of higher pressure, where molecules are squeezed closer together, is called a compression. But those compressed molecules don't stay bunched up. They push against the molecules ahead of them, passing the disturbance forward. And as they push forward, they leave behind a region where the molecules are now more spread out than normal. This region of lower pressure is called a rarefaction. So now you have a compression moving forward, followed by a rarefaction, and ahead of that compression, the same thing happens again. The compressed molecules push the next group of molecules forward, creating another compression, followed by another rarefaction. This pattern repeats over and over, spreading outward from your hands in every direction. This is a sound wave, not a thing, not a substance, a pattern of disturbance moving through matter. The air molecules themselves don't travel from your hands to someone's ear across the room. Each molecule just moves a tiny distance back and forth, bumping into its neighbor, which bumps into its neighbor, which bumps into its neighbor, passing the disturbance along like a chain reaction. It's exactly like a wave in a stadium. The people don't move from one side of the stadium to the other. Each person just stands up and sits down, but the wave itself travels all the way around. Sound works the same way. The molecules stay roughly where they are. The wave, the pattern of compressions and rarefactions, travels through them. This is why physicists call sound a mechanical wave. It's mechanical because it requires physical matter, real particles that can push against each other. And it's a wave because the disturbance propagates outward from its source as a repeating pattern through that matter. Without matter, without those particles to compress and rarefy, there is nothing to carry the wave. The pattern has no medium to move through. It simply doesn't exist. Let me make this even clearer with a different example. Imagine a long metal slinky stretched out on a table. If you push one end of the slinky forward, the coils at that end bunch together. That compression travels down the length of the slinky to the other end. You can see it move. The individual coils don't travel from one end to the other. They just push against their neighbors, and the disturbance propagates. If you pull the end back, the coils at that end spread apart, creating a rarefaction that also travels down the slinky. Push and pull rhythmically, and you get a continuous wave of compressions and rarefactions traveling through the slinky. That's exactly what sound is. A longitudinal wave, meaning the disturbance moves in the same direction as the waves travel, with regions of compression and rarefaction alternating as the wave moves through the medium. Now remove the slinky. Just push your hand forward into empty air. Wait. Not empty air. Just empty space. Nothing. No coils to compress. No medium to carry the wave. The push goes nowhere. The disturbance doesn't propagate because there's nothing to propagate through. That's space. But we're getting ahead of ourselves. Before we talk about space, let's go deeper into how sound works here on Earth. Because the details matter. Every sound you've ever heard was produced by something vibrating. Every single one, without exception. When you speak, your vocal cords vibrate. These are two small folds of tissue in your larynx, your voice box, and when air from your lungs passes through them, they open and close rapidly, vibrating at frequencies that depend on their tension, thickness, and length. A typical male voice vibrates at roughly 100 to 150 times per second, during normal speech. A typical female voice vibrates at roughly 200 to 300 times per second. When you change pitch, you're changing how fast your vocal cords vibrate. A higher pitch means faster vibration. Lower pitch means slower vibration. These vibrations push against the air molecules in your throat, creating compressions and rarefactions that travel up through your mouth and out into the room. Those pressure waves spread outward in all directions, eventually reaching someone else's ear. The fact that you can speak to another person across a room means that a continuous chain of molecular collisions is connecting your vocal cords to their eardrums. Billions upon billions of air molecules are passing the disturbance from one to the next, carrying the pattern of your voice through the air. When a guitar string is plucked, it vibrates back and forth. As it moves in one direction, it pushes air molecules together on that side, creating a compression. As it moves back, it leaves a rarefaction behind. The string vibrates at a specific frequency, determined by its length, tension, and thickness. A thicker string vibrates more slowly, producing a lower pitch. A thinner, tighter string vibrates faster, producing a higher pitch. The body of the guitar amplifies these vibrations, pushing more air and making the sound louder, but the fundamental process is the same. A vibrating object pushes air molecules, creating pressure waves that travel outward. When a drum is struck, the drum head vibrates. When a bell is rung, the metal vibrates. When a tuning fork is struck, the prongs vibrate. When thunder rumbles, it's because a bolt of lightning has superheated the air along its path to temperatures around 30,000 degrees Celsius, about 5 times hotter than the surface of the sun. This sudden extreme heating causes the air to expand violently, creating a massive pressure wave that travels outward as the sound we call thunder. Even thunder, as dramatic and powerful as it sounds, is just a pressure wave in the air. Just molecules pushing against molecules. The frequency of a sound wave determines its pitch. Frequency is measured in hertz, which simply means vibrations per second. A sound wave vibrating at 440 hertz is the note A above middle C, the standard tuning pitch used by orchestras around the world. A sound wave vibrating at 20 hertz is the lowest pitch most humans can hear. It is a deep, rumbling, almost primal bass that you feel almost more than you hear. A sound wave at 20,000 hertz is the highest pitch most humans can hear. A thin, piercing tone near the edge of perception. Below 20 hertz are infrasound waves, too low for us to hear but still physically real. Elephants communicate using infrasound at frequencies as low as 14 hertz, producing sounds that can travel miles across the African savanna. Above 20,000 hertz are ultrasound waves, too high for us to hear. Dogs can hear up to about 65,000 hertz, which is why a dog whistle works. Bats use ultrasound for echolocation, emitting pulses at frequencies up to 200,000 hertz and listening for the echoes to navigate in complete darkness. But regardless of frequency, regardless of whether it's infrasound or ultrasound or anything in between, the mechanism is the same. A vibrating source creates compressions and rarefactions in a medium, and those pressure fluctuations propagate outward as a wave. Change the frequency, and you change the pitch. Change the amplitude, the strength of the compressions, and you change the volume. But the fundamental nature of the wave doesn't change. It's always a mechanical disturbance in matter. The wavelength of a sound wave is the physical distance between two consecutive compressions or two consecutive rarefactions. Wavelength and frequency are inversely related. Higher frequency means shorter wavelength. Lower frequency means longer wavelength. A sound wave at 20 Hz has a wavelength of about 17 meters. That's roughly the length of a bowling lane. A sound wave at 20,000 Hz has a wavelength of about 1.7 centimeters, shorter than your little finger. The wavelength matters because it determines how sound interacts with objects. Low-frequency sounds with long wavelengths can bend around obstacles and travel through walls relatively easily. That's why you can hear the bass from a neighbor's stereo, but not the treble. The bass wavelengths are long enough to diffract around corners and through barriers. High-frequency sounds with short wavelengths are more easily absorbed and blocked. They don't bend around obstacles as well. This is why soundproofing materials are designed to absorb and scatter shorter wavelengths, and why your voice sounds muffled behind a closed door, but the bass from a party down the street comes through clearly. Now, let's talk about the speed of sound, because this is where the physics of the medium, the stuff the sound travels through, becomes crucial. In dry air at 20 degrees Celsius, about room temperature, sound travels at approximately 343 meters per second. That's roughly 1,235 kilometers per hour. Fast by human standards, but slow compared to many other things. Light, for example, travels at about 300,000 kilometers per second, roughly 875,000 times faster than sound. This is why you see lightning before you hear thunder. The light from the lightning bolt reaches your eyes almost instantly, but the sound takes several seconds to cover the same distance. For every 5 seconds between the flash and the thunder, the lightning is about 1.7 kilometers away. You can actually use this to estimate how far away a storm is, but the speed of sound isn't fixed. It changes depending on the medium. And this is a critical point. Sound doesn't travel at the same speed through everything. Its speed depends on two properties of the material it's moving through: the density of the material and its elasticity. Elasticity in physics refers to how quickly a material returns to its original shape after being deformed. A material with high elasticity springs back quickly. A material with low elasticity deforms and stays deformed. In general, sound travels faster through materials that are stiffer and denser in the right way. Sound in water travels at about 1,480 meters per second, more than 4 times faster than in air. This is because water molecules are much closer together than air molecules. When one water molecule is pushed, it immediately pushes its neighbor because the neighbor is right there, very close. The disturbance doesn't have to cross a large gap. It's transmitted almost instantly from molecule to molecule. Water is also much less compressible than air, meaning it springs back faster from compression. Both of these properties help sound travel faster. In steel, sound travels even faster at about 5,960 meters per second. That's more than 17 times faster than in the air. Steel molecules are packed tightly together in a rigid crystal lattice. When you compress one part of the lattice, the disturbance travels through the rigid structure incredibly quickly. This is why you can sometimes hear a train coming by pressing your ear to the rail long before you hear it through the air. The sound is traveling through the steel track at nearly 6 kilometers per second, while the sound through the air is poking along at 1/3 of a kilometer per second. In diamond, the hardest known natural material, sound travels at approximately 12,000 meters per second. That's about 35 times faster than in the air. The carbon atoms in diamond are bonded together in an extremely rigid tetrahedral crystal structure, making diamond one of the stiffest materials in existence. Disturbances travel through this structure with remarkable efficiency. If you could somehow tap one end of a diamond rod 1 meter long, the vibration would reach the other end in less than a 10,000th of a second. Even in something as simple as a wooden table, sound travels faster than in air, about 3,000 to 4,000 meters per second, depending on the type of wood and the direction of the grain. This is why if you press your ear against a table and someone taps the other end, the sound seems louder and sharper than if you lifted your head and listened through the air. You're hearing the sound transmitted through a denser, stiffer medium. The molecules in the wood are tightly bound together and pass vibrations along with far greater efficiency than loosely bouncing air molecules. These examples all illustrate the same principle. Sound needs matter to travel through, and the properties of that matter, how closely its particles are packed, how strongly they're bonded together, how quickly they spring back from compression, determine how fast the sound moves. The medium isn't just a passive carrier, it's an active participant. The nature of the medium shapes the sound, determines its speed, affects its volume, and influences how far it can travel. Now, here's something that will help you understand the silence of space. As you go higher in Earth's atmosphere, the air gets thinner. There are fewer molecules in each cubic centimeter. At sea level, as I mentioned, there are about 25 billion molecules per cubic centimeter. At the summit of Mount Everest, roughly 8,800 meters above sea level, the air pressure is about 1/3 of what it is at sea level. There are far fewer molecules in each cubic centimeter. Sound still travels at altitude, but it's noticeably weaker. There are fewer molecules to carry the wave, so the compressions and rarefactions are less pronounced. The wave loses energy more quickly because there are simply fewer particles to sustain it. If you tried to shout to someone at the summit of Everest, your voice would sound thin and weak compared to what it would sound like at sea level. Not just because of the wind, but because there are simply fewer air molecules to vibrate. Keep going up. At an altitude of about 100 kilometers, which is the Kármán line, the internationally recognized boundary where space begins, the atmosphere is so thin that there are only about 1 trillion molecules per cubic centimeter. That might still sound like a lot, but compare it to sea level. 1 trillion versus 25 billion. The air at the Kármán line is about 25 million times thinner than the air at sea level. At this altitude, sound waves can barely propagate. The molecules are so far apart that they rarely collide with each other. A compression can't form effectively because the molecules are too spread out to push against each other in a meaningful way. Go higher still, into low Earth orbit at about 400 kilometers, where the International Space Station orbits, and the atmosphere is even thinner. There might be only a few billion molecules per cubic centimeter. These molecules are so spread out that they travel long distances between collisions, sometimes kilometers. At this point, the concept of a sound wave becomes meaningless. You can't create a compression when the nearest molecule might be meters away. There's nothing to compress against. The medium has become so diffuse that it can no longer support mechanical waves. This brings us to a concept that's crucial to understanding the silence of space: the mean free path. This is the average distance a molecule travels between collisions with other molecules. At sea level, the mean free path is incredibly short, only about 68 nanometers. That's 68 billionths of a meter. Molecules at sea level are colliding constantly, billions of times per second, with their neighbors right next door. This is perfect for sound transmission. Compressions and rarefactions pass from molecule to molecule with ease because the next molecule is always right there. At the altitude of the International Space Station, the mean free path is on the order of kilometers. A molecule might travel 10 kilometers before bumping into another molecule. At this scale, sound waves simply cannot exist. You can't have a coordinate pattern of compressions and rarefactions when each molecule is kilometers apart from its neighbors. The whole concept of a pressure wave breaks down. There's no medium in any meaningful sense. There's just isolated molecules drifting through emptiness, occasionally bumping into each other by chance. Now, let's talk about how your ear actually works, because understanding how we perceive sound reinforces why a medium is essential. Your ear is essentially a mechanical device designed to convert pressure waves in air into electrical signals that your brain can interpret. It's an astonishing piece of biological engineering, fine-tuned by hundreds of millions of years of evolution. When sound waves reach your ear, they first enter the ear canal, a tube about 2.5 centimeters long that leads to the eardrum. The eardrum, also called the tympanic membrane, is a thin, cone-shaped membrane about 10 millimeters across. When the compressions and rarefactions of a sound wave reach the eardrum, they cause it to vibrate. The eardrum moves inward during compressions when the air pressure is slightly higher, and outward during rarefactions when the pressure is slightly lower. These movements are incredibly small. At the very threshold of hearing, the faintest sound you can detect, the eardrum moves less than 1 billionth of a centimeter. That's less than the diameter of a hydrogen atom. Yet your ear can detect this movement. Behind the eardrum is the middle ear, which contains 3 tiny bones, the smallest bones in the human body. They're called the malleus, incus, and stapes, commonly known as the hammer, anvil, and stirrup. These bones form a lever system that amplifies the vibrations from the eardrum and transmits them to the inner ear. The stapes, the smallest of the 3, is only about 3 millimeters long and weighs about 3 milligrams. It presses against a membrane-covered opening called the oval window, which leads to the inner ear. The inner ear contains the cochlea, a snail-shaped structure filled with fluid. When the stapes pushes against the oval window, it creates pressure waves in this fluid. Inside the cochlea, there's a structure called the organ of Corti, which contains about 15,000 tiny hair cells. These hair cells have microscopic projections on their tops. When the fluid pressure waves bend these projections, the hair cells generate electrical signals. Different hair cells respond to different frequencies. Hair cells near the base of the cochlea respond to high frequencies. Hair cells near the tip respond to low frequencies. This is how your brain distinguishes pitch. The electrical signals travel along the auditory nerve to the brain, where they're processed and interpreted as sound. The entire chain, from sound wave to conscious perception, is mechanical at every step. Air molecules push against the eardrum. The eardrum pushes against the bones. The bones push against the oval window. The oval window pushes against the cochlear fluid. The fluid pushes against hair cells. Only at the very last step, when the hair cells generate electrical signals, does the process become electrical. Everything before that is physical vibration, matter pushing against matter. This is why you can't hear in a vacuum. If there are no air molecules to push against your eardrum, the eardrum doesn't vibrate. If the eardrum doesn't vibrate, the chain of mechanical transmission never starts. Your ear is waiting for pressure waves that will never arrive. It's like having a perfectly functional telephone with no phone line connecting it to anyone. The phone works fine. The problem is that there's no connection, no medium to carry the signal from one end to the other. Think about this the next time you hear anything. When you hear someone's voice across a room, what's actually happening is that their vocal cords are vibrating, pushing air molecules in their throat. Those molecules are pushing against neighboring molecules, and this chain of molecular collisions is propagating across the room at 343 meters per second. Billions upon billions of air molecules are participating in this relay, each one moving just a tiny distance, just a fraction of a millionth of a meter, bumping into its neighbor, passing the disturbance forward. By the time this wave reaches your ear, it might have been carried by trillions of individual molecular collisions. And your eardrum picks up this faint pattern of pressure changes and converts it into the experience of hearing a voice. It's remarkable, it's mechanical, and it absolutely requires a medium. Every single sound you've ever heard, from the first cry when you were born to the last words someone said to you today, was carried to your ears by matter, by air molecules mostly, occasionally by water or solid materials, but always by something, always by a physical medium whose particles could compress and rarefy, could push against each other in a coordinated pattern, and could transmit a mechanical wave from source to listener. Remove that medium, and you remove sound entirely. Not because the vibrating source stops vibrating. A guitar string would still vibrate in a vacuum. Your vocal cords would still move, at least until the lack of air became a more pressing problem. The vibration still exists, but without molecules surrounding the source to be compressed and rarefied, the vibration goes nowhere. It stays local. It jiggles the source object and nothing else. No wave propagates, no chain reaction of molecular collisions spreads outward. No disturbance reaches your ear. There is only silence. Not the kind of silence you experience in a quiet room where there's still the faint hum of electrical systems, the whisper of air currents, the subtle sounds of your own body. That's just low volume sound. This is something completely different. This is the total physical absence of sound, the complete impossibility of pressure waves existing because there is nothing to carry them. And that's what space is. Not just quiet, not just very, very still, but fundamentally, structurally, and physically incapable of transmitting sound. And to understand why, we need to look closely at what space actually is, what it contains, what it doesn't contain, and why those trillions of molecular collisions that carry every sound you've ever heard simply cannot happen in the void between the stars. So, let's look at space. Let's look at what exists between the stars and between the planets and understand why this environment is so fundamentally hostile to sound that even the concept of a pressure wave becomes meaningless out there. When most people think of space, they think of emptiness, pure, absolute nothing. And while that's not entirely accurate, it's much closer to the truth than most people realize. The void between planets, between stars, between galaxies is the emptiest environment we know of. It's emptier than anything we can create in a laboratory on Earth. It's emptier than anything you've ever experienced or could ever experience on the surface of this planet. And it's that emptiness, that staggering absence of matter, that makes sound impossible. Let's start by understanding just how empty space actually is by comparing it to what we have here on Earth. At sea level, as we discussed, every cubic centimeter of air contains roughly 25 billion molecules. That's 25 followed by 18 zeros. Those molecules are packed closely together, separated by distances much smaller than the molecules themselves. They're constantly colliding, billions of times per second, bouncing off each other, transferring energy, maintaining the pressure that keeps your eardrums slightly pushed inward, that keeps your lungs inflated, that makes weather and wind and sound possible. Now consider this. The best vacuum chambers on Earth, the most sophisticated equipment that humanity has ever built for creating an absence of matter, can pump a chamber down to about 100 molecules per cubic centimeter. That's extraordinary when you think about it. Starting from 25 billion molecules and removing almost all of them until only about 100 remain in that same tiny volume. That's like draining an ocean and leaving behind a few drops. These ultra-high vacuum chambers are used in cutting-edge physics experiments, in the precision manufacturing of computer semiconductors, where even a single stray molecule can ruin a microchip, and in space simulation facilities where engineers test equipment that will eventually operate in the real vacuum of orbit. Even in these extreme laboratory vacuums, with only 100 or so molecules per cubic centimeter, sound cannot propagate in any meaningful way. There simply aren't enough particles to form a compression wave. The molecules are so far apart that they almost never collide with each other. Each molecule drifts alone through the chamber, occasionally bouncing off a wall, but almost never encountering another gas molecule. There's no medium. There are just isolated particles in a void. But here's what's remarkable. Space is far emptier than even our best vacuum chambers. Far, far emptier. In low Earth orbit, where the International Space Station circles the planet at about 400 kilometers altitude, there are roughly 1 billion molecules per cubic centimeter. That might sound like a lot until you compare it to sea level. Low Earth orbit has about 25 billion times fewer molecules per cubic centimeter than the air you're breathing right now. It's an extraordinarily thin atmosphere, so thin that spacecraft experience almost no drag. Almost. They actually do experience a tiny amount of drag from those sparse molecules, which is why the ISS needs periodic boosts to maintain its orbit. But for sound, this density is hopelessly inadequate. 1 billion molecules per cubic centimeter is still about 25 billion times thinner than sea level air. Far too sparse for meaningful pressure waves. Go farther out, beyond the thin wisps of Earth's extended atmosphere, into the space between planets. The interplanetary medium and conditions become even more extreme. The space between planets in our solar system contains roughly 5 to 10 particles per cubic centimeter at Earth's distance from the Sun. Not 5 to 10 billion. Not 5 to 10 million. 5 to 10. In the same volume that teems with life-sustaining air at sea level, there is one lonely atom. Think about how incomprehensibly empty that is. If you scaled up a cubic centimeter at sea level so that each molecule was the size of a grain of sand, the molecules would form a solid wall of sand packed tight with no gaps. If you did the same for interplanetary space, there would be 5 grains of sand in a volume the size of a large building. 5 grains in an entire building. And you're trying to make those 5 grains bump into each other in a coordinated wave pattern. It's not just difficult, it's physically impossible. Most of these particles in interplanetary space aren't even neutral atoms or molecules like the nitrogen and oxygen in our atmosphere. They're charged particles, mostly protons and electrons, streaming outward from the sun in a constant flow called the solar wind. The solar wind moves at speeds between 300 and 800 kilometers per second, far faster than any bullet or rocket on Earth, carrying the sun's magnetic field with it outward through the solar system. These particles are incredibly sparse and incredibly fast. They don't behave like the gas in a room. They don't bounce off each other in the same way that air molecules do at sea level. They interact primarily through electromagnetic forces, through the push and pull of electric and magnetic fields, rather than through direct physical collisions. The mean free path of a particle in the solar wind, the average distance it travels before interacting with another particle, can be enormous. Near Earth's orbit, it's on the order of 1 astronomical unit, roughly 150 million kilometers. A particle can travel the entire distance from the Earth to the Sun before meaningfully interacting with another particle. You cannot build a pressure wave out of particles that travel 150 million kilometers between interactions. The very concept breaks down. Now, go even farther out. Leave the solar system entirely. Enter the interstellar medium, the vast ocean of space between the stars. Out here, the emptiness becomes almost philosophical. In the general interstellar medium, there's roughly 1 atom per cubic centimeter on average. 1. In the same volume that teems with matter at sea level, there is 1 lonely atom. Usually it's a single hydrogen atom, the simplest and most abundant element in the known universe. Sometimes it's a helium atom, very rarely something heavier, but overwhelmingly it's hydrogen, drifting alone through the darkness, separated from its nearest neighbor by about a centimeter, which on atomic scales is an almost unimaginable gulf. Remember, atoms are about 1/10,000,000th of a meter across. A centimeter is 100 million times larger than a typical atom. It would be like a person standing alone in a space 100 million times their own height in every direction. That's roughly 170,000 kilometers, more than 13 times the diameter of the Earth. Imagine standing alone on a featureless plain that stretches to a horizon 170,000 kilometers away in every direction, and somewhere out there, equally alone, is one other person. That's the isolation of atoms in interstellar space. That's the environment you're asking to transmit a sound wave. One solitary atom drifting in darkness, with its nearest neighbor an incomprehensible distance away in relative terms. At this density, the mean free path of a particle, the distance it travels before bumping into another particle, is roughly 10 billion kilometers. That's about 67 times the distance from the Earth to the Sun. An atom in interstellar space could travel from the Sun to well past Pluto and back, dozens of times over, before encountering another atom. Under these conditions, talking about sound waves is like talking about ocean waves in a desert. The medium doesn't exist. There's nothing to compress, nothing to rarefy, nothing to carry a disturbance from one point to another. An atom vibrating in interstellar space vibrates alone. Its motion affects nothing around it because there's nothing around it to affect. But interstellar space isn't even the emptiest space that gets. Between galaxies in the vast voids of intergalactic space, the density drops even further. In the general intergalactic medium, there might be only 1 atom per cubic meter, not per cubic centimeter, per cubic meter. That's 1,000,000 times emptier than the already absurdly empty interstellar medium. 1 atom in a space about the size of a large refrigerator. Scale that up to human proportions, And you're talking about a single person alone in a volume of space larger than the orbit of Neptune. The mean free path of a particle in intergalactic space can be measured in light years. An atom could drift for years, even centuries, at enormous speed without ever encountering another atom. The intergalactic voids, those enormous empty regions between the filaments of the cosmic web, are the emptiest places in the known universe, and they are the most profoundly silent environments that exist. Not silent, the way we use the word on Earth. Silent in a way that transcends the concept. Silent because there is physically, fundamentally, nothing there to make or carry sound. This progression of emptiness, from the air around you to the upper atmosphere to low Earth orbit, to interplanetary space, to interstellar space, to intergalactic space, represents a continuous decline in the ability of the environment to carry sound. At each step, the medium becomes thinner, the particles become more scarce, the distances between them grow larger, and the possibility of coordinated pressure waves diminishes further. By the time you reach the void between galaxies, you've arrived at a place so empty that not only is sound impossible, but most physical processes that depend on particle interactions simply don't happen. Now, this understanding of sound and vacuum didn't come easily to humanity. For most of human history, nobody knew that sound needed a medium to travel through. Why would they? Sound seemed to travel everywhere on Earth. You could hear things through the air, through the water, through solid walls. It never occurred to most people that there might be an environment where sound simply couldn't exist. The ancient Greek philosopher Aristotle theorized that sound was a disturbance in air, which was remarkably insightful for the 4th century BCE, but he didn't have the tools to test this idea rigorously. The first real experimental evidence came in the 17th century. In the 1650s and 1660s, scientists began experimenting with vacuum pumps, devices that could remove air from sealed containers. Robert Boyle, the Irish-born natural philosopher often considered one of the founders of modern chemistry, performed a famous experiment in 1660 using an air pump designed by his brilliant assistant Robert Hooke. Boyle placed a ticking watch. Some accounts say it was a small bell inside a glass jar connected to the vacuum pump. With air in the jar, you could clearly hear the ticking. Then, he began pumping out the air. As the air grew thinner, the sound grew fainter. When most of the air was removed, the ticking became nearly inaudible. The watch was still ticking. You could see it through the glass. The mechanical parts were still moving. The vibrations were still occurring inside the watch. But without air to carry the sound, those vibrations couldn't reach the listener's ear. Boyle himself documented this with characteristic clarity, recognizing that it provided powerful evidence that air was not merely incidental to sound, but essential to it. This was a landmark moment in the history of science. It provided direct experimental evidence that sound requires a medium. The vibrating source alone isn't enough. You need something between the source and the listener to transmit the vibrations. In the absence of that something, there is silence. Boyle's experiment was somewhat limited by the technology of his time. His vacuum pumps couldn't remove all the air, so a very faint sound could still sometimes be detected. Better pumps were developed over the following centuries, and each improvement confirmed the same result. The less air in the jar, the fainter the sound. Remove enough air and the sound vanishes completely, even though the source continues to vibrate. Today, we can recreate this experiment with far more precision using modern technology. Vacuum chambers in 21st century laboratories can achieve pressures billions of times lower than what Boyle could manage with his hand-operated pump. And the result is the same, only more definitive and more dramatic. Place a speaker in a vacuum chamber, pump out the air, and you can watch the speaker cone vibrating through the glass or acrylic walls of the chamber. You can see it moving back and forth exactly as it would if it were producing thunderous sound, but there is no sound. Complete, total, absolute silence. The speaker is doing everything right mechanically. The cone is pushing forward and pulling back at the correct frequencies, at the correct amplitudes. The electrical signal driving the speaker is unchanged from what it was when the chamber was full of air. But without air molecules to push against, the speaker cone is just moving back and forth in emptiness. It's pushing against nothing. The vibrations go nowhere. The energy of the cone's motion is slowly converted to heat in the speaker itself rather than being transmitted outward as sound. This experiment has been performed thousands of times in physics classrooms around the world, and it never fails to make an impression on students seeing it for the first time. A ringing bell under a glass jar, cheerfully clanging away, slowly falling silent as the air is pumped out. The bell doesn't stop moving. You can see it swinging, but the sound fades and then vanishes. It's elegant, it's clear, and it illustrates a profound truth about the physical universe. Sound is not a property of the vibrating object. Sound is a property of the medium through which vibrations travel. Remove the medium, and you remove the sound, even though the vibration remains perfectly intact. Let me push this further because I want you to really internalize why this matters. Imagine you could take the loudest sound ever produced on Earth and try to produce it in space. The loudest sound in recorded human history is generally considered to be the eruption of Krakatoa in 1883. When this Indonesian volcano erupted on August 27th of that year, it produced a sound that was heard nearly 5,000 kilometers away, on the island of Rodriguez in the Indian Ocean. People there reported hearing what sounded like distant cannon fire. The pressure waves circled the entire Earth, not once, but at least 3 or 4 times, detected by barographs at weather stations around the world for days after the event. The sound at the source was estimated at about 310 decibels, which is extraordinarily loud. For reference, a jet engine at close range produces about 150 decibels, a rock concert about 115 decibels, and the threshold of pain for the human ear is about 120 to 130 decibels. The decibel scale is logarithmic, which means 310 decibels isn't just twice as loud as 155. It's trillions upon trillions of times more powerful. The pressure wave from Krakatoa was so forceful that it ruptured the eardrums of sailors on ships more than 60 kilometers away. It generated tsunami waves that killed tens of thousands of people, and it blew out windows at a distance of hundreds of kilometers. Now, imagine that same eruption happening in the vacuum of space. What would you hear? Nothing. Absolutely nothing. Not a faint whisper. Not a muffled rumble. Nothing at all. The force of the eruption would still exist. If the volcanic material hit something, a rock, a spacecraft, it would deliver a physical impact. The light from the eruption would be visible. The heat would radiate outward. But the sound, that devastating pressure wave that circled the planet, would not exist. There would be no air to compress, no medium to form a pressure wave. The explosion would be visually spectacular but acoustically non-existent. This is perhaps the most vivid way to understand the silence of space. An explosion powerful enough to be heard 5,000 kilometers away on Earth would be completely, perfectly, absolutely silent in space. Not because the explosion is any less powerful, but because there is nothing out there to carry the sound. The medium is missing. And without the medium, there is no wave. This leads to a point that's worth emphasizing. The silence of space isn't about volume. It's not that space is very quiet. Quiet implies that there is some sound, just not very much of it. A library is quiet. A forest at dawn is quiet. These environments have sound, just at low levels. Space doesn't have low levels of sound. Space has no sound at all in the vast regions between objects. The distinction is fundamental. Quiet is a matter of degree. Silence in space is a matter of physics. It's the complete absence of the conditions necessary for sound to exist. You couldn't make space louder by shouting harder, building a bigger speaker, or detonating a bigger bomb. No amount of energy turned into vibration will produce sound if there's nothing to vibrate. There's another misconception worth addressing. Some people assume that because space contains some particles, sparse as they are, sound must travel through space, just very slowly or very faintly. This seems logical on the surface. After all, if interstellar space has 1 atom per cubic centimeter, and if atoms can collide, shouldn't there be some extremely faint, extremely slow version of sound propagation? The answer is complicated, but for all practical purposes, no. For a sound wave to exist as a coherent phenomenon, the wavelength of the wave has to be significantly larger than the mean free path of the particles in the medium. This is a requirement, not a suggestion. If the wavelength is shorter than the mean free path, particles don't collide often enough to pass the disturbance along coherently. The wave breaks down. Individual particles fly off on their own trajectories without coordinating their motion into a collective pattern of compressions and rarefactions. They're not acting as a medium. They're acting as isolated projectiles. In the interstellar medium, with a mean free path of roughly 10 billion kilometers, only sound waves with wavelengths vastly larger than 10 billion kilometers could theoretically propagate. That means wavelengths on the order of light years. Such a wave would have an extraordinarily low frequency, cycles that take thousands or millions of years to complete, an amplitude so vanishingly small that they'd be undetectable by any conceivable instrument. It would be less like sound in any recognizable sense, and more like a barely perceptible statistical fluctuation in particle density spread across light years of space. Calling it sound would be stretching the definition beyond recognition. In practice, scientists do study density fluctuations in space plasmas, the ionized gases that fill certain regions of space. These fluctuations can exhibit wave-like behavior, and they're sometimes loosely described as sound waves in popular science writing. But they're fundamentally different from the sound you hear on Earth. They propagate through ionized plasma rather than neutral gas. They're governed by electromagnetic forces as much as by particle collisions. Their frequencies are far below anything a human ear could detect, even in principle, and their wavelengths can span the distance between planets or even between stars. They're not something you could ever hear. They're a mathematical description of pressure variations in an incredibly sparse plasma, and they belong to a branch of physics called magnetohydrodynamics, rather than the acoustics you learned about in high school. Let me bring this closer to human experience to help you understand what an astronaut actually encounters. When an astronaut goes on a spacewalk, stepping outside the International Space Station into the vacuum of space, they are surrounded by silence. Not the silence of a quiet room, not the muffled silence you experience when you put on noise-cancelling headphones. A silence more profound and more absolute than any they've ever experienced, or will ever experience on the surface of Earth. If they could remove their helmet, which they obviously never do because the vacuum would kill them in minutes, they would hear nothing. If a meteor struck the station 10 meters away, they would see the impact, see the debris, feel the vibration if it traveled through the structure they were holding onto, but they would not hear it through the vacuum separating them from the impact. This is actually a serious safety consideration for space agencies around the world. On Earth, we rely heavily on sound for situational awareness, often without even realizing it. We hear alarms, hear machinery malfunctioning, hear unusual rattles or grinding noises that signal something is wrong, hear structural failure, and hear approaching danger. These auditory cues are so deeply wired into our survival instincts that we respond to them before we've even consciously registered what we've heard. A sudden loud crack makes you flinch before you know what caused it. That's millions of years of evolution keeping you alive through sound. But in the vacuum outside a spacecraft, all of these auditory cues vanish completely. An astronaut on a spacewalk cannot hear a warning, shout from a colleague, cannot hear the hiss of escaping air that might indicate a suit breach, cannot hear the mechanical sounds that might signal a problem with their equipment. They must rely entirely on visual cues, on radio communications, on the readings of instruments built into their suits. Sound, that most basic and instinctive of human warning systems, is completely useless outside the thin shell of the spacecraft. Inside the suit, of course, the astronaut can hear just fine. Their suit is pressurized with air, creating a small bubble of atmosphere around their body. Their breathing is audible. The hum of the suit's life support systems is audible. Radio communications are played through speakers inside the helmet. All of these are sounds transmitted through the air inside the suit, but the sounds stop at the suit's outer surface. The vibrations in the suit's air push against the inside of the helmet and the suit fabric, but those vibrations don't propagate outward into the vacuum beyond. The suit is an island of sound in an ocean of silence. Radio communication between astronauts and mission control works perfectly in space, but this often confuses people. If space is silent, how can astronauts talk to each other across vast distances? The answer is that radio waves are not sound. They are electromagnetic radiation. They're fundamentally different from sound waves in every physical respect. Radio waves don't need a medium to propagate. They're self-sustaining oscillations of electric and magnetic fields that travel through empty space at the speed of light. When an astronaut speaks into their radio, their voice vibrates a microphone that converts the mechanical vibrations of air into an electrical signal. That electrical signal is used to modulate a radio wave, which is then broadcast through space. The radio wave travels through the vacuum effortlessly, requiring no particles, no medium, no matter of any kind. When it reaches a receiver on another astronaut's suit or at mission control on Earth, it's converted back into an electrical signal, which drives a speaker, which vibrates air molecules inside the room or helmet, recreating the sound. At no point in this process does sound travel through space. Sound is created in the astronaut's helmet, converted into electromagnetic radiation, transmitted through the vacuum as a radio wave, received at the destination, and converted back into sound. The space between the sender and receiver carries no sound at all. It carries electromagnetic radiation, which is a completely different physical phenomenon. And this distinction between sound and electromagnetic radiation is absolutely essential to understanding why you can't hear in space, but you can see in space, why you can't shout across the void, but you can send a message across the void. It's not that space blocks communication, it's that space only blocks one specific type of wave, the mechanical kind, while allowing another type, the electromagnetic kind, to pass through freely. This is such an important distinction that it deserves its own deep exploration. And we're going to get into exactly that, examining what electromagnetic waves are, how they differ from sound, and why this difference explains so much about how we experience and explore the universe. Because here's the thing, the universe isn't silent in every sense. It's only silent in one very specific sense, the mechanical sense, the sense that involves matter pushing against matter. Strip that away, strip away the medium, and you strip away sound. But you don't strip away everything. Light still travels, radio waves still travel, X-rays, gamma rays, infrared, ultraviolet, all of these still travel through the emptiest reaches of space as though the vacuum weren't even there. The vacuum that completely and utterly stops sound has absolutely no effect on light whatsoever. And understanding why this is the case will reveal one of the most beautiful and fundamental divisions in all of physics. The division between waves that need the universe's matter to exist and waves that need nothing at all. So let's explore that division. Because understanding the difference between sound and light, between mechanical waves and electromagnetic waves, is one of the most important ideas in all of physics. And it explains not just why space is silent, but why we can see across the universe while hearing almost nothing beyond our own atmosphere. We've established that sound is a mechanical wave. It requires matter. It requires particles that can be compressed and rarefied, particles that can push against each other and pass a disturbance from one to the next. Without those particles, sound cannot exist. This is the absolute, unbreakable rule of acoustic physics. No medium, no sound, no exceptions. But light is completely different. Light is an electromagnetic wave. And electromagnetic waves don't need matter at all. They don't need particles. They don't need a medium. They can travel through a perfect vacuum, through the emptiest space imaginable, through the void between galaxies where there's barely one atom per cubic meter, and they arrive at their destination completely intact. Light doesn't care whether there's matter in its path or not. It travels through matter, and it travels through emptiness with equal ease. The vacuum that utterly destroys sound doesn't even slow light down. In fact, light travels fastest in a vacuum, faster than it travels through any material substance. To understand why, you need to understand what light actually is, and this is where physics gets genuinely beautiful. Light is a self-propagating disturbance in electric and magnetic fields. That might sound abstract, so let me break it down. Electric and magnetic fields exist everywhere in the universe. They're fundamental properties of space-time itself. An electric field is a region where electric charges would feel a force. A magnetic field is a region where moving charges or magnets would feel a force. These fields aren't made of matter. They're not made of particles in the ordinary sense. They're properties of space itself. They exist, whether or not there's any matter present. In the 1860s, a Scottish physicist named James Clerk Maxwell made one of the greatest intellectual achievements in the entire history of human thought. Working largely with mathematics and theoretical insight rather than laboratory experiments, Maxwell unified electricity and magnetism into a single coherent theory, showing that they weren't separate forces operating independently, but two intertwined aspects of the same fundamental phenomenon, electromagnetism. Maxwell's equations, a set of four elegant and remarkably compact mathematical relationships, described exactly how electric and magnetic fields interact with each other and with charged particles. But Maxwell discovered something extraordinary buried within his equations. When he combined them in a certain way, they predicted that a changing electric field would create a magnetic field, and that a changing magnetic field would create an electric field. These two fields could sustain each other in a self-perpetuating cycle. An oscillating electric field would generate an oscillating magnetic field, which would generate an oscillating electric field, which would generate an oscillating magnetic field, on and on forever, each one creating the other in an endless dance, and this self-sustaining oscillation would move through space as a wave. Maxwell calculated the speed of this wave from his equations. The speed depended only on two fundamental constants of nature: the permittivity of free space and the permeability of free space. These constants describe how electric and magnetic fields behave in a vacuum. When Maxwell plugged in the known values of these constants, he got a speed of approximately 300,000 kilometers per second. He immediately recognized this number. It was the speed of light, which had already been measured experimentally. This was a thunderbolt moment in physics. Maxwell had shown that light was an electromagnetic wave. The light that enters your eyes. The light from the sun that warms your skin. The light from distant stars that astronomers study through telescopes. All of it is oscillating electric and magnetic fields propagating through space at 300,000 kilometers per second. And crucially, nothing in Maxwell's equations required a medium. The wave didn't need particles to propagate. It didn't need anything to push against or compress or rarefy. The electric and magnetic fields sustained each other through empty space, creating and recreating each other as they traveled. This is the fundamental difference between sound and light. Sound is a disturbance in matter. Light is a disturbance in fields. Matter can only exist in certain places, wherever particles happen to be. But electric and magnetic fields exist everywhere, even in a perfect vacuum. So light can travel everywhere. It has no need for molecules, atoms, or any physical substance. It carries its own medium with it, so to speak, in the form of the electromagnetic fields that permeate all of space. Actually, even saying it carries its own medium isn't quite right, because that implies there's a medium separate from the wave itself. There isn't. The wave is the medium. The oscillating electric and magnetic fields are both the wave and the thing the wave travels through. There's no distinction between the carrier and the carried. This is profoundly different from sound, where the wave and the medium are separate things. Air molecules are the medium. The pattern of compressions and rarefactions is the wave. You can have the medium without the wave, which is just still air, and you can't have the wave without the medium. But with light, the wave is everything. It needs nothing else. It is entirely self-contained. This is why you can see stars that are billions of light years away. The light left those stars billions of years ago and has been traveling through the vacuum of space ever since, crossing unimaginable distances of almost perfect emptiness. It passed through interstellar space, through intergalactic voids, through regions where there might be 1 atom per cubic meter or less. and it arrived at your eye or a telescope's detector carrying information about the star that emitted it. The photons didn't need anything between the star and your eye except empty space. The vacuum was all they needed because they didn't need a medium at all. Now, light is just one kind of electromagnetic radiation. The electromagnetic spectrum is vast, spanning an enormous range of frequencies and wavelengths, and all of it travels through vacuum at the speed of light. The only difference between the various types of electromagnetic radiation is their frequency and wavelength. Radio waves have the longest wavelengths and lowest frequencies. A typical FM radio wave has a wavelength of about 3 meters and a frequency of about 100 million hertz, or 100 megahertz. Radio waves are used for broadcasting, for communication with spacecraft, for radar, for Wi-Fi, for Bluetooth, and for cell phones. Every time you make a phone call, send a text message, or connect to the internet wirelessly, you're using electromagnetic waves that travel at the speed of light and need no medium whatsoever. Microwaves have shorter wavelengths than radio waves, typically between 1 millimeter and 30 centimeters. Your microwave oven uses electromagnetic waves at a frequency of about 2.45 gigahertz, which happens to be a frequency that's efficiently absorbed by water molecules. The microwaves cause water molecules in your food to vibrate faster, generating heat. Microwaves are also used in satellite communications and in radar systems. Infrared radiation has wavelengths shorter than microwaves but longer than visible light, roughly between 700 nanometers and 1 millimeter. You can't see infrared with your eyes, but you can feel it as heat. When you hold your hand near a hot stove without touching it, you're feeling infrared radiation. Every warm object emits infrared radiation, including your own body. Infrared telescopes can see through dust clouds that block visible light, revealing hidden stars and galaxies. Visible light occupies a remarkably tiny sliver of the electromagnetic spectrum, with wavelengths between about 380 and 700 nanometers. This narrow band is the only part of the vast electromagnetic spectrum that human eyes evolved to detect. Red light has the longest wavelengths of visible light, about 700 nanometers. Violet light has the shortest wavelength, about 380 nanometers. In between, arranged by decreasing wavelength, are orange, yellow, green, and blue. When you see a rainbow, you're seeing white light from the sun separated into its component wavelengths by water droplets in the atmosphere, each wavelength bending at a slightly different angle. Ultraviolet radiation has wavelengths shorter than visible light, between about 10 and 380 nanometers. The sun emits a significant amount of ultraviolet radiation. Most of it is absorbed by Earth's ozone layer, which protects life on the surface from its damaging effects. Ultraviolet radiation can break chemical bonds in DNA, which is why too much sun exposure can cause skin cancer. It's also why certain organisms have evolved to use pigmentation as protection, and why sunscreen works by absorbing or reflecting ultraviolet wavelengths before they reach your skin. X-rays have even shorter wavelengths, between about 0.01 and 10 nanometers. They're produced by extremely hot gases and by violent cosmic events like supernova explosions and material falling into black holes. X-ray telescopes in orbit, like the Chandra X-ray Observatory, observe some of the most energetic phenomena in the universe. On Earth, we use X-rays in medical imaging because they can pass through soft tissue but are absorbed by dense structures like bones. This is possible because X-rays are electromagnetic waves. They travel through the vacuum of space to reach orbiting telescopes, and they travel through the air and through your body in a doctor's office. No medium required for the travel itself. The interaction with matter at the destination is a separate process from the propagation of the wave through space. Gamma rays have the shortest wavelengths and highest frequencies of all electromagnetic radiation, with wavelengths smaller than an individual atom. They're produced in nuclear reactions, in the superheated cores of exploding stars, in the violent swirling disks of material falling into black holes, and in other extraordinarily extreme cosmic events. Gamma ray bursts, brief but incredibly intense flashes of gamma radiation from distant galaxies, are the most energetic events in the known universe. A single gamma ray burst can release more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. These bursts travel across billions of light years of empty space to reach our detectors. Billions of light years of vacuum, and the gamma rays arrive perfectly intact, carrying information about cataclysmic events that happened in the distant past, in the distant universe. Every single type of electromagnetic radiation, from the longest radio waves to the shortest gamma rays, travels through the vacuum of space at the same speed, 300,000 kilometers per second, the speed of light. This speed is a fundamental constant of the universe, woven deeply into the very structure of space-time itself. It doesn't depend on the frequency or wavelength of the radiation. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays all travel at exactly the same speed through a vacuum. They differ only in frequency and wavelength, but their speed is identical. This is why we can observe the universe at all. Everything we know about the cosmos beyond our own planet comes from electromagnetic radiation that has traveled through the vacuum of space to reach us. Every image of a distant galaxy, every measurement of a star's temperature, every map of the cosmic microwave background, every detection of a gamma ray burst, all of it is based on electromagnetic waves that cross the void of space without needing any material substance to carry them. Contrast this with sound. If sound were our only way of sensing the universe, we'd know almost nothing about what's out there. We'd be able to hear events on Earth, and we could potentially hear through Earth's atmosphere out to its upper boundary. But beyond that, silence. Total silence. No information from the moon, from the sun, from other planets, from other stars. The universe beyond our atmosphere would be completely, utterly inaccessible to us through sound. We'd be trapped in our small world, surrounded by a vast cosmos that we could never hear. Electromagnetic radiation freed us from that trap. Light showed us the stars. Radio waves let us communicate with spacecraft. X-rays revealed the violent hearts of galaxies. Infrared lets us peer through dust clouds to see stellar nurseries where new stars are being born. Gamma rays showed us the most powerful explosions in the universe, all because electromagnetic waves don't need a medium, and sound does. Now, this distinction between mechanical and electromagnetic waves confused physicists for a surprisingly long time. In the 19th century, even after Maxwell showed that light was an electromagnetic wave, most physicists assumed there had to be some kind of medium carrying it. They called this hypothetical medium the luminiferous ether. The word luminiferous means light-bearing. They imagined the ether as a substance that filled all of space, invisible and intangible, but capable of supporting the oscillations of light waves, just as air supports the oscillations of sound waves. This seemed perfectly reasonable at the time. Every wave they knew about needed a medium. Water waves needed water. Sound waves needed air. It seemed logical that light waves must also need something. The search for the ether consumed decades of scientific effort. If the ether existed, and if Earth was moving through it as it orbited the sun, then the speed of light should vary depending on which direction you measured it. Light traveling in the same direction as Earth's motion through the ether should appear slightly slower, like swimming against the current. Light traveling against Earth's motion should appear slightly faster, like swimming with the current. The difference would be small, but measurable with precise enough instruments. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an incredibly precise experiment to detect this difference. They built a device called an interferometer that split a beam of light into two beams traveling at right angles to each other, reflected them, and recombined them. If one beam was traveling with Earth's motion through the ether and the other was traveling perpendicular to it, the two beams should return at slightly different times, creating a measurable interference pattern. The experiment was extraordinarily sensitive. It could detect differences in the speed of light as small as a few kilometers per second, easily enough to detect the expected effect of Earth's orbital velocity of about 30 kilometers per second. Michelson and Morley ran the experiment repeatedly, at different times of day, at different times of year, rotating the apparatus to check every possible direction. The result was always the same, no difference. The speed of light was identical in every direction, regardless of Earth's motion. There was no ether wind, no sign that Earth was moving through any kind of medium. This null result was one of the most important experimental findings in the history of physics. It showed that the ether didn't exist. Light didn't need a medium. It traveled through empty space at a constant speed that was the same for all observers, regardless of their motion. This result was deeply puzzling at the time, but it became one of the foundations of Albert Einstein's special theory of relativity, published in 1905, which revolutionized our understanding of space, time, and the nature of light. Einstein showed that the speed of light in a vacuum is the same for every observer, no matter how fast they're moving or in what direction. This is the second postulate of special relativity, and it has been confirmed and reconfirmed by over a century of increasingly precise experiments conducted around the world. The speed of light isn't just a speed that light happens to travel at. It's a fundamental property of space-time, a cosmic speed limit that nothing with mass can reach. And it requires no medium to exist at that speed. The vacuum of space is not an obstacle for light. It's the natural environment for light. Light was born to travel through nothing. This understanding completely resolves the apparent paradox of space being simultaneously silent and visible. Sound and light are fundamentally different types of waves. Sound is a mechanical wave requiring matter. Light is an electromagnetic wave requiring nothing but the fields that permeate all of space. The vacuum of space eliminates the medium for one while being the perfect medium, or rather the perfect absence of impediment for the other. Let me connect this directly to space exploration, because this is where the distinction between sound and electromagnetic radiation becomes practical rather than just theoretical. Nearly every piece of information humanity has ever gathered from beyond our atmosphere was carried by electromagnetic radiation. The overwhelming majority of it, from visible starlight to radio transmissions from spacecraft. When the Voyager spacecraft, now over 24 billion kilometers from Earth, sends data home, it uses radio waves. Those radio signals travel at the speed of light through the vacuum of interplanetary space, requiring no medium, no relay stations, no physical connection of any kind between the spacecraft and Earth. The signal weakens with distance because it spreads out over an increasingly large area. But it doesn't degrade because of the vacuum. The vacuum is not the problem. Distance is the problem. The vacuum itself is perfectly transparent to the signal. When the James Webb Space Telescope observes a galaxy 13 billion light-years away, it's collecting infrared photons that have been traveling through the vacuum of space for 13 billion years. Those photons left their source when the universe was young, when the first galaxies were just forming, and they've been crossing the expanding void ever since. 13 billion years of travel through some of the emptiest space in the universe, and they arrive at the telescope's mirror carrying detailed information about the galaxy that emitted them. Their wavelength, their intensity, the pattern of absorption lines in their spectrum, all of this data survived the journey intact because electromagnetic radiation doesn't need matter to carry it. When the Mars rovers send photographs back to Earth, those images are encoded as radio signals that cross the gulf between Mars and Earth at light speed. Depending on where Mars and Earth are in their orbits, this distance ranges from about 55 million to 400 million kilometers. The radio signals need no medium for this journey. They travel through the interplanetary void as easily as they travel through the air in your living room. More easily. In fact, because the vacuum offers no absorption, no scattering, no interference, just pure, unimpeded propagation. When astronomers detect gravitational waves from colliding black holes or neutron stars, they're using a different kind of signal entirely, one that's not electromagnetic, but is also able to travel through empty space. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity and first detected directly in 2015 by the LIGO experiment. Like electromagnetic waves, gravitational waves don't need a material medium. They propagate through the vacuum at the speed of light, carrying information about the most violent events in the universe across billions of light years of empty space. Sound could do none of this. If we relied on mechanical waves to explore the universe, we would know nothing about anything beyond our own atmosphere. We wouldn't know the sun is a star. We wouldn't know that other stars exist. We wouldn't know about galaxies or black holes or the cosmic microwave background or the expansion of the universe. Our entire picture of the cosmos, everything we've learned about the universe beyond our own planet, comes from electromagnetic radiation's ability to cross the vacuum. That sound cannot. This brings me to a point that's worth emphasizing because it's a common source of confusion. When people hear sounds associated with space, whether it's in a science fiction movie, a NASA press release, or a planetarium show, they sometimes think those sounds were actually recorded in space. They weren't. Those sounds fall into several categories, and understanding these categories helps clarify the relationship between electromagnetic radiation and sound. First, there are pure movie sound effects. When you hear explosions in Star Wars or engine roars in Star Trek, those sounds are entirely fictional. They're added for dramatic effect because a silent explosion, while scientifically accurate, isn't very exciting in a movie theater. Filmmakers know that space is silent, They add sound anyway because movies are entertainment, not physics lectures. The roar of the Millennium Falcon's engines, the thunderous boom of the Death Star exploding, the whoosh of a TIE fighter screaming past, none of these sounds could actually exist in the vacuum of space. They're artistic choices, not scientific ones. Second, and this is where it gets more interesting, there are sounds from NASA and other space agencies that are real data converted into audio. These are called sonifications. The process works like this. A spacecraft or telescope detects electromagnetic radiation, radio waves, X-rays, infrared, whatever it's designed to observe. Scientists then take the electromagnetic data and map it onto audio frequencies, converting it into sound that human ears can hear. The result is something you can listen to through speakers or headphones, but it's not a recording of sound in space. It's a translation. It's electromagnetic data that has been converted into a different format for human perception. For example, in 2022, NASA released audio derived from data collected by the Chandra X-ray Observatory around a massive galaxy cluster called Perseus. Headlines declared that NASA had recorded sound in space, and the audio clip went viral. But what actually happened was more nuanced. The Perseus galaxy cluster contains vast clouds of hot gas between its galaxies. Pressure waves do ripple through this gas, and in a technical sense, these are acoustic phenomena, vibrations propagating through a medium. But the frequency of these waves is extraordinarily low, about 57 octaves below middle C. Far too low for any human ear to ever detect, even if you were floating inside the gas cloud. What NASA did was take the X-ray data that revealed these pressure waves, shift the frequency up by 57 octaves into the range of human hearing, and release the resulting audio. It's a brilliant way to make scientific data accessible and engaging, but it's not a microphone recording of sound in space. It's a creative translation of electromagnetic observations into an audio format. Similar sonifications have been done with data from the Sun, from Jupiter's magnetosphere, from Saturn's radio emissions, from pulsars, and from many other cosmic sources. In every case, the original data is electromagnetic, not acoustic. Radio waves from Jupiter's radiation belts are converted to audio. X-ray fluctuations from a pulsar are mapped onto sound. Plasma wave data from the Voyager spacecraft are shifted into audible frequencies. These are all fascinating and often eerily beautiful, but they are translations, not recordings. The distinction matters because it reinforces the fundamental point. Space doesn't transmit sound. What space transmits are electromagnetic signals. And we clever humans have figured out how to take those signals and convert them into sounds we can hear, giving our ears access to information that was never acoustic in the first place. The Voyager plasma wave instrument is a particularly interesting example. As Voyager crossed from the solar system into interstellar space, its plasma wave instrument detected oscillations in the plasma surrounding the spacecraft. These oscillations, caused by the interaction between the solar wind and the interstellar medium, occur at frequencies within or near the range of human hearing. When scientists converted the electrical signals from the instrument directly to audio, without any frequency shifting, the result was an eerie, rising tone that corresponded to increasing plasma density as Voyager moved into interstellar space. This was widely reported as the sound of interstellar space, and in a loose sense, that's not entirely wrong. The plasma oscillations are real physical vibrations in a medium, the thin plasma of the interstellar boundary. But even here, what the instrument detected were electrical oscillations in the plasma, not pressure waves hitting a microphone. The data was electromagnetic in nature. It was then played through a speaker to create sound waves in a room on Earth. At no point did acoustic sound travel through the vacuum from the source to the listener. Understanding all of this, the difference between mechanical and electromagnetic waves, the absence of a medium in space, the creative translations that turn data into sound brings us to a natural question. If the vacuum of space prevents sound from traveling between objects, are there places in the universe where sound does exist? Are there environments beyond Earth where the air, or something like air, is thick enough to carry actual pressure waves from one place to another? And the answer, as it turns out, is yes. Sound is not exclusive to Earth, it just needs the right conditions, and those conditions do exist in some remarkable places across the solar system and beyond. Let's start with the most obvious place where sound exists beyond Earth's surface, inside the spacecraft, because this is a point that often gets lost in the popular understanding of sound and space. When people say you can't hear anything in space, that's true for the vacuum between objects, but inside a spacecraft, inside a space station, inside an astronaut suit, there is air. And where there is air, there is sound. The International Space Station is one of the noisiest workplaces in the solar system. Astronauts who have lived aboard the station consistently report that one of the biggest challenges of daily life in orbit is the constant background noise. The station is filled with fans, pumps, air processors, ventilation systems, computers, and dozens of other machines, all running continuously to keep the crew alive. Air doesn't circulate naturally in microgravity. On Earth, warm air rises and cool air sinks, creating natural convection currents that move air around a room. In the weightlessness of orbit, this doesn't happen. Without fans constantly blowing air through the station, astronauts could suffocate in a pocket of their own exhaled carbon dioxide. So fans run all the time, everywhere, and fans make noise. The noise level on the ISS typically ranges from about 60 to 72 decibels in the habitable modules. That's roughly the volume of a normal conversation up to the volume of a vacuum cleaner running continuously. Some modules, particularly those with older equipment, can be louder. The sleep stations where astronauts rest are designed to be quieter, but even there, the hum of the station's machinery is always present. NASA and its international partners have worked for decades to reduce noise levels on the station, because long-term exposure to constant noise causes hearing damage, disrupts sleep, increases stress, and reduces the crew's ability to communicate effectively. Astronauts on the ISS routinely wear earplugs, especially when sleeping or working near particularly noisy equipment. All of this sound exists because the ISS is pressurized. The interior of the station contains a breathable atmosphere maintained at roughly the same pressure as sea level on Earth. This atmosphere, about 78% nitrogen and 21% oxygen, just like on the ground, provides the medium that carries sound from the fans, pumps, and machines to the astronauts' ears. Sound waves propagate through the station's air just as they would through the air in your living room. The physics is identical. Compressions and rarefactions travel through the gas at roughly the same speed they would on Earth. But the sound stops at the station's walls. The whole of the ISS separates the pressurized interior from the vacuum of space. Sound waves inside the station hit the inner surface of the hull, and some of that energy is absorbed. Some is reflected into the station, but virtually none of it passes through the hull and into the vacuum beyond. The vacuum outside doesn't transmit the vibration. So from the outside, the station is silent, a massive structure the size of a football field, humming and buzzing with life and machinery on the inside, but acoustically dead on the outside. 2 astronauts could float 5 meters apart on the exterior of the station during a spacewalk, and neither would hear a sound from the other unless they used their radios. There's an interesting nuance here though. While sound can't travel through the vacuum between 2 astronauts on a spacewalk, it can travel through solid structures. If both astronauts are holding onto the same handrail on the station's exterior, and one of them taps the rail, the other might feel the vibration through their gloves and potentially even hear it faintly. The vibration would travel through the metal of the handrail as a mechanical wave, cross into the astronaut's glove, through the suit material, and into the small pocket of air, inside the glove and suit, eventually reaching their ear. It would be very faint, but it would be physically possible. Sound can travel through solids in space because solids are a medium. The atoms in a metal handrail are tightly bonded together. A vibration at one end propagates through the crystal lattice to the other end, just as it would on Earth. The vacuum between the rail and the astronaut's ear is bypassed, because the solid provides a continuous path for the mechanical wave. This principle extends beyond spacecraft. Any solid object in space can transmit vibrations internally. An asteroid tumbling through the void is acoustically silent on its exterior, surrounded by vacuum. But if something struck that asteroid, a micrometeorite for example, the impact would generate vibrations that would travel through the asteroid's rocky body as seismic waves. If you could somehow stand on the asteroid's surface with your helmet pressed against the rock, you might hear or feel those vibrations transmitted through the solid material into your helmet and then into the air inside your suit. The vacuum surrounding the asteroid stops sound from radiating outward into space, but inside the solid body itself, mechanical waves propagate just fine. The same is true for moons and planets with solid surfaces. The moon has no atmosphere, so its surface environment is essentially a vacuum. There's no air to carry sound between 2 points on the lunar surface. But the moon's interior can transmit seismic vibrations. The Apollo astronauts left seismometers on the moon's surface, and these instruments detected moonquakes for years after the missions ended. Some of these quakes were caused by meteorite impacts. Others were caused by thermal expansion and contraction as the moon's surface heated and cooled through its long day-night cycle, which lasts about 29.5 Earth days. Still others were deep moonquakes, caused by tidal forces from Earth's gravity flexing the moon's interior. All of these events generated mechanical waves that traveled through the moon's solid body. They were real vibrations, real mechanical waves, traveling through a real medium. The moon's rocky interior carried them efficiently across hundreds of kilometers. But those vibrations never became sound in the way we experience it because there was no atmosphere on the surface to convert them into audible pressure waves. They remained locked inside the solid body of the moon, detectable only by instruments pressed directly against the surface. Now, let's go somewhere truly fascinating. Let's visit other worlds in our solar system that have atmospheres, because these are places where genuine sound, real pressure waves traveling through a gaseous medium actually exist. Venus is the closest planet to Earth in size, but its atmosphere is nothing like ours. The Venusian atmosphere is almost entirely carbon dioxide. About 96.5%, with clouds of sulfuric acid floating at altitudes between 45 and 70 kilometers above the surface. The atmospheric pressure at the surface of Venus is about 92 times greater than Earth's sea level pressure. That's equivalent to the pressure you'd experience roughly 900 meters deep in Earth's oceans. The temperature at the surface averages about 465 degrees Celsius, hot enough to melt lead. In this thick, dense, scorching atmosphere, sound would travel remarkably well. In fact, sound would travel faster on Venus than on Earth. The speed of sound depends on the temperature and composition of the gas, and the extremely high temperatures on Venus would push the speed of sound to roughly 410 meters per second, compared to about 343 meters per second on Earth. The dense atmosphere would also carry sound with less attenuation, meaning sounds would travel farther before fading. If you could somehow survive on the surface of Venus, which you couldn't because the heat, pressure, and acid would destroy any human or any machine we've ever built within hours, you would find it a very noisy place in principle. The dense atmosphere would transmit sound extremely efficiently. Your voice would sound higher and strangely distorted because of the faster speed of sound and the crushing density of the gas, but it would carry clearly and far. No human has ever heard the sound of Venus, and no microphone has ever recorded it. The Soviet Venera landers that reached the surface in the 1970s and 80s survived for only about 30 minutes to 2 hours before succumbing to the extreme conditions. They sent back photographs and atmospheric measurements, but they didn't carry audio recording equipment. Future missions might change that. There have been proposals for Venus landers carrying microphones, but the engineering challenges are extraordinary. Any microphone would need to survive temperatures hot enough to melt tin and zinc, pressures equivalent to the deep ocean, and an atmosphere laced with corrosive sulfuric acid. That's a tall order for a delicate acoustic instrument. Mars is a completely different story. While Venus has an atmosphere that's far too thick and hostile, Mars has an atmosphere that's almost too thin. The Martian atmosphere is about 95% carbon dioxide, but it's incredibly thin. The surface pressure on Mars is only about 600 pascals, less than 1% of Earth's sea level pressure. That's roughly equivalent to the pressure at an altitude of 35 kilometers on Earth. Well into the stratosphere, a height where no human could survive without a pressure suit. Despite this incredibly thin atmosphere, sound can still propagate on Mars. The atmosphere isn't a vacuum. There are still molecules there, still particles that can be compressed and rarefied. But sound on Mars is very different from sound on Earth. Because the atmosphere is so thin, sound is much quieter. A sound that would be clearly audible at a certain distance on Earth would be barely perceptible at the same distance on Mars. The thin atmosphere simply can't carry as much acoustic energy. It's like the difference between shouting across a crowded room and shouting across a mountaintop. The same vocal effort produces a much weaker result when there are fewer air molecules to work with. The speed of sound on Mars is also different. Because of the lower temperature, which averages about minus 60 degrees Celsius, and the different atmospheric composition, sound travels at only about 240 meters per second on Mars. That's about 30% slower than on Earth. This means that if you could stand on the Martian surface without a suit and clap your hands, the sound would reach a person 10 meters away about 12 milliseconds later than it would on Earth. A small difference, but a measurable one. And here's where things get genuinely exciting. We've actually heard what Mars sounds like. In February 2021, NASA's Perseverance rover landed in Jezero crater on Mars carrying 2 microphones. One was part of the SuperCam instrument on the mast, and the other was mounted on the rover's body. These microphones captured the first ever audio recordings made on the surface of another planet. The results were extraordinary and scientifically revealing. Perseverance recorded the sound of Martian wind, a thin, eerie whisper compared to wind on Earth. It recorded the sound of the rover's own wheels crunching over Martian rocks and gravel. It recorded the sharp crack of the SuperCam laser hitting a rock target, a sound that scientists could analyze to learn about the rock's properties. And it recorded the buzzing hum of the Ingenuity helicopter's blades as the small drone flew through the thin Martian air, the first ever recording of a powered aircraft on another world. These recordings confirmed several predictions about Martian acoustics. Sounds on Mars are indeed quieter than on Earth. High-pitched sounds are absorbed more quickly by the carbon dioxide atmosphere. So what you hear on Mars has a slightly muffled quality, as though someone turned down the treble. Scientists also discovered something unexpected. Sound travels at 2 different speeds on Mars depending on its frequency. Low-frequency sounds travel at about 240 meters per second, but high-frequency sounds above about 240 hertz travel faster at about 250 meters per second. This frequency-dependent speed of sound, which is negligible on Earth, means that on Mars, a complex sound like music would arrive at your ears garbled. The high-pitched notes would arrive before the low-pitched notes, distorting the timing and harmony. A symphony performed on Mars would sound subtly wrong to any listener standing even a modest distance from the musicians. It would be out of sync with itself. Now let's travel to what might be the most acoustically interesting world in the entire solar system. Titan, Saturn's largest moon. Titan is the only moon in the solar system with a thick atmosphere. In fact, Titan's atmosphere is thicker than Earth's. The surface pressure on Titan is about 1.5 times Earth's sea level pressure. If you stood on Titan's surface, there would be 50% more atmosphere pressing down on you than at sea level on Earth. You wouldn't need a pressure suit to survive the atmospheric pressure, though you definitely need protection from the extreme cold and the unbreathable nitrogen-methane atmosphere. Titan's atmosphere is predominantly nitrogen, roughly 98%, with about 1.5 to 5% methane depending on altitude, along with traces of other hydrocarbons like ethane and propane. The surface temperature hovers around minus 179 degrees Celsius, cold enough for methane to exist as a liquid. Titan has lakes and seas of liquid methane and ethane, the only body in the solar system besides Earth known to have stable surface liquid. It rains liquid methane on Titan. Rivers of methane have carved channels across the landscape. It's like a bizarre frozen echo of Earth's water cycle, except everything is made of hydrocarbons. In this thick, cold, nitrogen-rich atmosphere, sound would propagate easily. In fact, sound transmission on Titan would be excellent. The thick atmosphere provides plenty of molecules to carry pressure waves. The speed of sound on Titan would be significantly slower than on Earth, only about 194 meters per second, because of the extremely low temperature. Remember, the speed of sound in a gas depends on temperature. Colder gas means slower molecular motion, which means slower sound propagation. What would Titan sound like? Your voice on Titan would sound dramatically different from how it sounds on Earth. The lower speed of sound would lower the resonant frequencies of your vocal tract, making your voice sound deeper. But the denser atmosphere would also change how your vocal cords vibrate. The combined effect would make you sound like a deep bass version of yourself. If two people could somehow stand on Titan's surface and have a conversation, they would sound strange to each other, deeper, slower, and with a quality unlike anything they'd ever heard on Earth. In January 2005, the European Space Agency's Huygens probe descended through Titan's atmosphere and landed on its surface. As it fell through the thick nitrogen haze, instruments on the probe recorded data about atmospheric conditions. The Huygens Atmospheric Structure Instrument measured temperature, pressure, and density as the probe descended. Scientists have used this data to reconstruct what sounds on Titan would actually be like. They've created simulations of what thunder, wind, and splashing liquid methane would sound like in Titan's atmosphere. The results are hauntingly alien, deeper and more resonant than their earthly equivalents, carried efficiently through the dense, cold air. These other worlds remind us that sound isn't unique to Earth. It's unique to environments that have a medium, a gas, a liquid, or a solid, through which mechanical vibrations can propagate. Earth happens to have an atmosphere that's particularly well suited to the kind of sound we've evolved to hear. But sound itself is a universal physical phenomenon that occurs wherever the conditions are right. Venus has sound, Mars has sound, thin, quiet, and strange, but real. Titan has sound, deep and slow and alien, but real. Even the gas giants, Jupiter and Saturn, have atmospheres where pressure waves propagate. Deep inside Jupiter's massive atmosphere, where pressures and temperatures rise to extreme levels, acoustic waves travel through hydrogen and helium gas that gradually transitions into a liquid state. The boundary between gas and liquid is blurred at those pressures, but mechanical waves travel through it all. So the statement that you can't hear anything in space needs a qualification. You can't hear anything through the vacuum of space. The emptiness between worlds is genuinely silent in the acoustic sense. But the worlds themselves, the planets and moons and spacecraft and space stations, these are islands of sound in the cosmic silence. Wherever there is matter dense enough to transmit vibrations, sound exists. And those islands are scattered throughout the solar system and presumably throughout the universe, on every world that has an atmosphere or a solid body capable of transmitting mechanical waves. This brings us to something deeper, something worth reflecting on as we close this journey through the physics of sound and silence. The fact that you can't hear anything in space tells us something profound, not just about space, but about ourselves. We are creatures of our medium. Every sense we have evolved to work within the specific conditions of Earth's surface. Our eyes evolved to see the narrow band of electromagnetic radiation that passes through Earth's atmosphere and is reflected by the objects around us. Our ears evolved to hear the pressure waves that travel through Earth's air at the frequencies produced by the things that mattered for our survival. The rustle of a predator in the grass, the crack of a breaking branch, the cry of a child, the voices of our companions. Our entire sensory world is tuned to this planet's specific conditions. Take us off this planet, remove the atmosphere that carries sound to our ears, and one of our most important senses becomes useless. In the vacuum of space, your ears are perfectly functional organs with nothing to do. They're waiting for pressure waves that will never come. Your eardrums are still there, ready to vibrate. Your ossicles are still there, ready to amplify. Your cochlea is still there, ready to convert vibrations into electrical signals. But the chain is broken at the very first link. There is no medium to deliver vibrations to your eardrum. Your hearing, honed by millions of years of evolution, refined to extraordinary sensitivity, capable of detecting eardrum movements smaller than the diameter of a hydrogen atom, is rendered completely useless by the simple absence of air. This is humbling. It reminds us that our senses don't show us the universe as it really is. They show us a narrow slice of reality, the slice that was useful for surviving as primates on the African savanna. We see only a tiny fraction of the electromagnetic spectrum. We hear only a narrow range of frequencies. We feel only a limited range of temperatures and pressures. The universe is vastly richer and more complex than our senses can perceive. There are phenomena happening all around us right now. Radio waves passing through your body, cosmic rays striking the atmosphere, neutrinos streaming through the earth that you cannot sense at all. Your senses evolved to keep you alive on this specific planet, in this specific atmosphere, under these specific conditions. They were never designed to perceive the full complexity of the cosmos, and yet, through science, through careful observation and reasoning and experimentation, we've extended our senses far beyond their biological limits. We've built radio telescopes that can detect electromagnetic whispers from the edge of the observable universe. We've built X-ray telescopes that can see the violent glow of matter falling into black holes. We've built gravitational wave detectors that can feel the ripple of space-time caused by colliding neutron stars billions of light years away. We've built microphones that can record the sound of wind on Mars and the crunch of alien gravel beneath a rover's wheels. We've translated the electromagnetic signals of the cosmos into sounds we can hear, giving our ears access to information they were never evolved to perceive. In a sense, science has given us new senses. It has expanded the boundaries of what we can know and experience far beyond the limitations of our biology. We can now perceive, through our instruments, phenomena that no biological organism could ever sense directly. We can see in wavelengths that no eye can detect. We can hear through sonification the oscillations of cosmic plasmas that no ear could ever register. We've overcome the limitations of our evolved senses through ingenuity and curiosity, two qualities that are, in their own way, just as remarkable as the senses themselves. The silence of space is not a flaw. It's not a deficiency of the universe. It's simply a consequence of what sound is and what space is. Sound is a mechanical wave that requires matter. Space is a vacuum that lacks matter. The two are fundamentally incompatible. But that incompatibility has pushed us to develop other ways of perceiving the cosmos, ways that don't depend on pressure waves in air. We've learned to read the electromagnetic spectrum like a book, extracting information from every wavelength, from the longest radio waves to the shortest gamma rays. We've learned to listen to the universe in ways our ears never could, using instruments that convert electromagnetic signals into data that our brains can interpret and understand. The next time you look up at the night sky, take a moment to appreciate the profound silence hanging above you, beyond the thin blue veil of our atmosphere, beyond the layer of air that carries every sound you've ever heard. There is a silence more complete than anything you've experienced on Earth. The stars you see are burning furnaces of nuclear fusion, producing temperatures of millions of degrees and pressures that would crush any material we know. but you can't hear them. The galaxies you might glimpse on a dark night are vast spinning collections of hundreds of billions of stars, each one a sun, many with their own planets, but you can't hear any of it. The universe is playing the grandest symphony imaginable. Stars being born, stars dying in supernova explosions, black holes consuming matter, galaxies colliding and merging, cosmic filaments stretching across billions of light years. But it's all happening in silence, at least in the acoustic sense. The vacuum between these objects carries no sound. The pressure waves that would let your ears participate in this cosmic drama have no medium through which to travel. And yet, through the electromagnetic radiation that crosses the void effortlessly, we know it's all happening. We can see it. We can measure it. We can understand it. We've built an entire picture of the cosmos. 13.8 billion years of history, 2 trillion galaxies, 200 billion trillion stars, all understood through radiation that doesn't need a single molecule of air to reach us. The silence of space hasn't stopped us from learning the universe's deepest secrets. If anything, it's forced us to develop better tools, better instruments, better ways of perceiving reality than our biological senses alone could ever provide. Sound is precious precisely because it's local. It exists only where matter exists, only where molecules can jostle and push and compress against each other. It's a phenomenon of proximity, of substance, of the tangible physical world. Every sound you hear is a reminder that you're surrounded by matter, by air, by a medium that connects you to the vibrating world around you. When you hear someone's voice, you're connected to them by a continuous chain of molecular collisions, stretching from their vocal cords to your eardrum. When you hear music, you're experiencing a pattern of pressure waves, sculpted by human creativity and transmitted through the air that you share with the musician. Sound is intimate, it's physical. It's an experience that exists only because you and the source of the sound are both immersed in the same ocean of air. Space has no such ocean. The void between the stars is dry. It carries light and radiation and gravitational waves, but it doesn't carry the gentle, mechanical, molecule-to-molecule vibrations that constitute sound. And that's why, when you step outside Earth's atmosphere, you step into a silence that is not just deep or profound, but absolute. A silence that isn't waiting to be broken. A silence that cannot be broken. Because the very mechanism of sound has no foothold in the emptiness between worlds. You can't hear anything in space, not because space is quiet, not because the universe lacks energy or violence or drama, but because sound is a physical, mechanical, material phenomenon. The vacuum of space has no material to carry it. That simple fact, a fact you can demonstrate with a bell jar and a vacuum pump, extends across the entire cosmos, from the space just above your head to the void between galaxy clusters billions of light years away. Wherever there is a vacuum, there is silence. Wherever matter gathers into atmospheres and oceans and solid ground, sound returns as it does on Mars, on Venus, on Titan, inside the International Space Station, and here on Earth, the world whose atmosphere has carried every sound you've ever known. So tonight, wherever you are, take a moment to listen. Really listen. To the wind outside your window, to the hum of your home, to the distant murmur of the world going about its business. These are sounds carried to you by the thin shell of gas that clings to this small, rocky planet. They are sounds that exist only because you live in a place where molecules are plentiful enough to vibrate, to compress, to rarefy, to carry the delicate patterns of pressure waves from one place to another. In the vast majority of the universe, this doesn't happen. Out there, in the immense dark void between the stars, there is only silence. The light of distant suns crosses that void easily, carrying stories of nuclear fire across the ages. But sound stays home. Sound stays where the air is. Sound stays where matter is. And right now, on this small world, in this thin atmosphere, surrounded by the sounds of life, that's exactly where you are. Thank you for joining me on this journey through the science of sound and the silence of space. If you found this exploration valuable, a like or a subscribe would mean a lot. It helps me keep making these deep dives into the way the universe works. And the next time someone tells you that in space, no one can hear you scream, you'll know exactly why. Not because space is far away, not because space is cold or dark or hostile, but because sound is a mechanical wave. The vacuum of space has nothing for that wave to travel through. The silence of space is not a mystery. It's physics. Beautiful, elegant, inescapable physics. Good night. And listen well. While you still have the air to carry every sound,